Hello. Hope you can hear me. Okay. Uh, we Means only two people have joined today, but okay, if more join in the course of time, we'll see. Uh, okay, so we'll this week what was primarily covered in the lectures was frequency and time selectivity, that notion, and also some more things. So we'll discuss some problems related to that. So, uh, so I hope you can hear me and see the screen. Would be good if somebody confirms in the chat. Okay, thank you. Uh, Fine. So, let us understand the key concept or the key topic here. So there are two axes along which the channel can vary, right? So this is a typical diagram that you can draw. There is a frequency axis and there is a time axis, right? And so what you typically know is uh, for for a for a channel, you will typic um, like you don't know about the channel, but let's say you know about the signal that you are transmitting. So for the signal, you will typically know the symbol rate or the like the time period, TS. So the time taken to transmit a particular symbol. And so let's say this is coherence time, uh, coherence time, let's say PC. And this is something like coherence bandwidth, BC. Right? So there are two parameters here. Firstly, so you have the channel, and there are two properties of the channel, AC and DC, right? And then you have the signal. And the signal has two properties, symbol time, and you also have the signal band, right? So something like bandwidth signal, right? The signal bandwidth, let's say, the BS. So we can actually divide this space into, uh, let me just draw this a little bit more symmetric. Need not be symmetric, but just for aesthetic purposes. So we can divide this kind of area into four parts. And that is the key idea here. So, uh, so how do we interpret this kind of curve? So if your channel, uh, so if your coherence time is smaller than the symbol period, right? If your coherence time is smaller than the symbol period, then what you have is a fast fading channel. Fast fading channel. So FF stands for fast fading, right? Because what does fast fading mean? Fast fading means that so coherence time TC is time that you uh, roughly the time period for which you can kind of assume that the time delay or time period for which you can assume that the channel has not changed or has not changed significantly enough. So if that time period is smaller than the time taken to transmit a signal, transmit a full signal, it means that before you have completed transmitting the signal, so this is the case where fast fading, the condition for fast fading is therefore Ts greater than Tc. And similarly, slow fading, it will be the opposite condition, Ts less than Tc. So this is slow fading. And I can repeat it over above also. So essentially, if in the duration that we can take examples also, let's say Ts is equal to 1 millisecond and like Ts equal to 1 millisecond and Tc equal to 0.5 millisecond, right? Something like that. So what does this mean? That you take 1 millisecond of time to send the signal from transmitter to like to send the signal out from your transmitter. In the time that you send the signal, the channel has already fluctuated significantly because it has gone through two coherence intervals. So we can roughly assume that the channel is constant for one coherence interval, but we can see that Ts is greater than Tc. So this is a fast fading channel because the channel has already fluctuated. The channel has already fluctuated by the time you are finishing the transmission of the signal. The reverse case, so if Ts equal to 0.5 millisecond and let's say Tc equal to 1 millisecond. So here, this is actually a slow fading case. Why? Because we are transmitting the signal for 0.5 millisecond and the channel will remain constant for 1 millisecond. So in the duration that we have transmitted the signal, so it's like in the duration we are transmitting signal for 0.5 millisecond, we can assume that the channel has not changed that much. So this is slow fading. Is this clear? And similarly, in the frequency domain, we have frequency flat, like okay, I'm using bad notation here, but I hope you get it. Frequency flat, and this is when the sampling frequency is when this is the when the symbol bandwidth is less than the coherence bandwidth, right? And the other part is frequency select. So this is when so this is frequency selective. What do you mean by frequency selective? By frequency selective, you know that the signal that you are transmitting has a certain bandwidth, Bs, right? And then and we also know that the channel has a coherence bandwidth that is a certain range of Doppler shift, a certain range of frequency shifts for which the channel does not change as much. The channel does not change as much, which is Vc, right? And if this sampling frequency is higher than the coherence bandwidth, it means that like so here also we can take example. Let's say sampling frequency is something like 10 megahertz and coherence bandwidth is something like 5 megahertz, which means that the signal occupies 10 megahertz bandwidth. And in this period, in this spread of the spectrum, the channel has already changed significantly because coherence bandwidth is 5 megahertz. That means if you go more than this, the channel has already changed. So So the channel is not uniform for this transmission, for transmission of the signal. The channel is not uniform across frequency because the frequency spread of the signal is more than the coherence bandwidth. And so here we see that Bs is greater than Bc, which means that it is frequency selective. In the opposite case, if the sampling frequency is smaller than the coherence bandwidth, it means that the not sampling frequency, signal bandwidth, it means that the signal bandwidth lies within that range for which we can consider the channel to be roughly constant, right? The channel has not fluctuated too much. So this is the case where Bs is less than Bc. So this is frequency flat. So we can just populate this. Bs greater than Bc will be frequency selective, and Bs is less than the coherence bandwidth would be frequency flat. I hope this kind of makes sense. If there are any doubts, please let me know now, because this is kind of the crux on which this whole week is based.
Sir, what is the meaning of this frequency selective and frequency fast?
Frequency flat and selective, right? So by that, what I mean is that your channel is, let's say, has an impulse response, right? Like basic signals and systems. Here is your input, here is your channel, or here is your system, and here is your output, right? So you write y of t equal to x of t convolution of h of t, something like this. In Fourier, if you take Fourier transform, then you will have something like x of f, h of f, y of f, right? This is upon taking Fourier transform. And equivalently, you write h of f. Now, so typically, this impulse response of the channel is a function of frequency, right? H of f. Now, let's say you want to transmit a signal x of f over this channel h of f. So you need an idea of the channel, right? And so for that, you need to know also whether h of f is, h of f. So we are actually talking about h of f here, which is a frequency representation of the channel. And so here, like for h of f, we need to see if this is constant for range of x of f, or so this is so constant, which means roughly, like, let's say, since this is multiplied, right? See, x of f can be some signal like this. Let's say this is x of f, right? Something like, yeah, minus w to w. So this is x of f. So we want to know if h of f, if the impulse response on the channel, so does it look like this? Does h of f look like this? Maybe it's like a box later, or we don't know. But essentially, we are considered about this part. Minus w to w. Is h of f roughly constant? Roughly. So then we can just, then we'll call it, essentially, we can roughly call it independent, right? Independent of it, roughly, of frequency. Or in other words, frequency flat. Frequency flat, right? On the other hand, you can also have h of f to be, fluctuating in this range, right? Something like this. So this can be another edge of it. So here it is in the second case.
Sir,
Uh,
excuse me, sir.
yeah,
Sir, means channel will provide constant response to the signal, na? In earlier case, means
yeah,
cons-
yeah, yeah,
constant for range of those frequencies, means for those frequencies channel is providing same response.
exactly. Yes. So in that
Uh,
cases, you will call it a frequency flat channel.
okay,
And in this
okay,
case, in the later case, since not constant, since the channel response is clearly not constant, then you will call it frequency selective, right? So which means different part. Uh, yeah, BS is sorry, BS is not sampling frequency. This is signal bandwidth. BS is signal bandwidth. My bad, I used the wrong term there. BS is signal bandwidth. So as you can see here in the diagram also I'm showing, right? This is the signal bandwidth that I'm talking about. And what I'm interested here is that for this signal bandwidth, do I have the channel response constant, or is the channel going to fluctuate in this bandwidth? So if the channel fluctuates in this bandwidth, then the gain that I'm receiving from the channel, this h of f, will depend on the value of f. So it depends on the exact value of f. So that's why it is frequency selective, which means it will favor some frequencies and not favor some other frequencies. That is selective of frequency. Does this make sense?
sir,
Uh,
but how it will happen means for means channel will be how channel will be frequency selective means channel is our signal is getting transmitted wirelessly. That means this
yeah,
surrounding is the channel, and
yeah.
then how it will be selective for some specific frequencies, and how it will be providing constant for some for all frequencies in both cases. How it will
So
happen, sir?
these are two different situations, right? Both can happen. It depends on the situation.
Huh?
It depends on the situation. So both can happen. Like, you want to know how frequency selectivity happens? Is that your question?
Yeah, 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 yeah.
So, so, so frequency selectivity can happen for many reasons. Uh, in especially the most common reason is Doppler effect.
Huh?
Doppler effect. So for Doppler effect, you have phase shifts, right? Something like e to the power j 2 pi fd Doppler frequency times t. So this term Doppler frequency, this changes the carrier frequency also, right? So so then your carrier frequency term is modified by plus minus md, or like, yeah. So so this can cause some frequencies to be like, maybe originally the channel was frequency flat, but because of high velocity motion, like Doppler effect as we know is the fluctuation of the carrier of the frequency because of speed. So if velocity is high, then there will be huge Doppler effect, which will lead to the channel getting fluctuating a lot more rapidly in the frequency domain, right? So uh, so that so that is one reason. Doppler effect can be a reason. Another reason can be in terahertz frequency. Sometimes, like in high frequency, sometimes you have molecular absorption in the environment. So uh, because of some frequencies in the signal, maybe it is causing resonance in the environment, like it's syncing up with the molecular vibrations in the environment, and so that helps some frequencies that hurt some other frequencies. So so that kind of various reasons are there for which many channels can frequency selective also. So how will you, like, as a like, you are not able, like, you're not a physicist, so you won't know always. But what we can do is we can measure channels, and we can measure. We will have an idea of coherence bandwidth, which is what is the range, um, what is the variation in frequency for which, um, what is the variation in frequency for which my channel roughly remains constant or doesn't fluctuate that much. Specifically, like, let's say you have some kind of, um, like yeah. So here, as you can see that you can only construct a very small box. Maybe let's do it a little less like this. So maybe this kind of a box, this kind of a small box is your coherence bandwidth, where your channel response is not fluctuating too much. So that is basically what you compare. You are trying to compare uh, the bandwidth or the frequency range for which your channel is not fluctuating too much with the signal bandwidth. So if your signal bandwidth, so as you can see here, like here you have a very small coherence bandwidth, right? BC is very small, and BC is less than the signal bandwidth. So if this happens, then the channel becomes frequency selective. Some frequencies are amplified, some frequencies are attenuated, right? Or less amplified. But if the channel, in the first case, for example, the channel looked like a flat line, almost like a flat line, maybe not exactly like this, but like a little bit squiggly is okay. The channel roughly stays constant for the duration of for the bandwidth of the signal. So that means in frequency domain, HF is almost independent of F. So you can basically here write YF equal to some H times X of F that you can write. So later, if you see MIMO expressions, this is one very common MIMO expression, like Y equal to HX plus M. So here we typically make narrow band assumption and H is frequency flat. But yeah, that's for later. But yeah, this is the key concept: frequency flat and frequency selective. Uh, so so again, there are four important values here. One is the symbol time, that is like signal time period of the signal itself. Then is the coherence time. So you have these two quantities of the channel and the signal in time domain. And in the frequency or the bandwidth axis, you have the signal's bandwidth and the channel's coherence bandwidth. And depending on their interdependence, you will characterize the channel as fast fading, slow fading, frequency flat, frequency selective. So that is the key message of the whole exercise that we'll be doing.
Sir, excuse me, sir.
Yeah.
Yeah, sir, it is clear now that channel can be frequency selective and channel can be frequency constant.
Yeah.
But then why particularly in these cases it will happen when TS, that is sample time, is greater than coherence time,
Yeah.
um, then only frequency selective.
No, no, no. Frequency selective is happening in both cases, right? So, uh, yeah, frequency selectivity is not dependent on time. So if the
Uh,
coherence bandwidth is smaller than the signal bandwidth,
uh,
then it will be frequency selective, irrespective of the time relation. But then
uh.
in time you have to see whether it is whether it is fast fading or slow fading. So that is a different thing, fast fading and
Uh-huh.
slow fading.
Okay. Sir, so what is the exact meaning of this coherence bandwidth and coherence time, sir? These concepts are not clear.
Coherence time is essentially your channel. any channel's behavior is a function of time, is a function of time also, right? Like a channel can fluctuate. A channel can fluctuate with respect to time axis, and it can also, because of multipath, the path delays. That is the like the time difference between the various multipaths. That also affects the channel, and the time delay of the channel. And so this is why it affects. So let's say you take measurements. Since like if this you convert to frequency domain, it actually this tau part converts into frequency domain, and then you have something like this. And this can be a little confusing, but yeah, that's how it is. And then anyway, but see what happens is see this frequency part. Hope you understood that. Like if you look at the channel from frequency domain, then you are trying to see what frequencies are reliably transmitted and what frequencies are not that reliably transmitted. In time domain, also, like a channel can vary with time, right? So maybe now it has a certain behavior. Maybe 10 seconds later, it will have a different kind of behavior. So you want to see how quickly the channel is changing its behavior, even at the same frequency level. Even at the same frequency level, you want to figure out how quickly the channel is changing its behavior. So that is why time dependence is also important. And so here in coherence time, you are trying to see for how long. Let's say here coherence time 1 millisecond means that roughly for 1 millisecond of duration, I can assume that the channel will not change. The channel will roughly remain uh, the same, will roughly retain the same behavior. After 1 millisecond, the channel's behavior will start changing. So because of various reasons, like might be temperature or environmental factors, whatever, the channel's behavior can change after 1 millisecond. So that is the coherence time. And then if the coherence time is and signal time is like the time period of the signal itself. And so in the time that is taken to transmit one signal, if the channel has already changed in that period, it means that we are in the duration of the signal transmission, we are observing not one but multiple channels because the channel has changed already. So that is the case of fast fading. That is the case of fast fading, where in one transmission, the signal has already changed multiple times. So we are not observing a single channel, but rather some kind of expected channel or some kind of statistic of the channel because the channel is fluctuating. Whereas in slow fading, we can assume that the channel is constant for the time that I'm transmitting signals. So that this case is a little easier to handle. Sometimes that we can assume that the channel has not changed for the time that I've transmitted the signal. So that is a time aspect. Does that make sense? Not?
Sir, means coherence time means how quickly channel is changing.
Yeah.
Yeah, okay. And coherence bandwidth means
Like in frequency response of channel, so coherence bandwidth is when you take frequency response of channel, then at any given time, if you take the frequency response of the channel, then uh, how does it behave with respect to frequency? Like like does it like what is the frequency like yeah what is the frequency fluctuation of the channel? Like
so
is it
how is the frequency response? That
yeah of the channel? So coherence bandwidth is essentially you are trying to find out what um, like what? Till what extent your channel is not fluctuating? Like in frequency domain, till what extent your channel is not fluctuating?
Okay, to what extent channel is not fluctuating in
Yeah,
frequency domain? That
yeah,
means
yeah,
for how much frequencies channel is not fluctuating from F1 to F2. If channel is not fluctuating, that means
yeah.
that F2 minus F1 will be the coherence bandwidth.
Not exactly. So F1 to F2. So then coherence bandwidth will basically be half of this. So this is like minus bandwidth and plus bandwidth, right? So coherence bandwidth in this case will be F2 minus F1 by 2. So that
Coherence
is
bandwidth is what, sir?
F2 minus F1 by 2. Like,
Okay, F2 minus F1 by 2.
yeah. So like bandwidth, right? So you're trying to see it like a signal with center frequency is 0. Like you're trying to compare it with the signal, right? So coherent bandwidth is essentially, yeah. So this, let's say you have some signal like this, F1, F2, not much fluctuations. Then your coherence bandwidth will be F2 minus F1 by 2.
Okay. Okay, sir. So it is to be calculated like this: F2 minus F1 by 2.
Yeah, typically you won't be asked to calculate the coherence bandwidth like this. You'll be given the value of coherence bandwidth because, yeah, it might not be just two signals, it will be multiple signals and it's a bit complicated. So typically you'll be given the value of coherence bandwidth.
Okay,
These
sir.
are, yeah,
Okay, thank you, sir.
okay. This is just for conceptual understanding. So let's say you are given now, so you have this kind of schematic. You are given something like you are told that your signal, let's say mark this question one, your coherence time Tc is equal to something like zero point 0.5 millisecond, and coherence bandwidth is equal to coherence bandwidth is equal to 1 megahertz, let's say, right? So this you are actually provided, and you are given that the signal bandwidth, uh, the symbol rate, let's say here, the symbol rate Rs is equal to something like um, let me change this to something like zero point 0.2. The symbol rate is given as 2 kilo symbols per second, and the bandwidth, the signal bandwidth is given to be, let's say, 2 megahertz, or like 1.9 megahertz, right? Now you have to tell if, now you have to essentially tell me about the channel. So let's say some question like describe the channel. Describe the channel in the sense that you have to tell me, whether it's frequency flat or frequency selective or fast fading or slow fading. Where does it lie in this scheme? So I'll leave the question here. Give you 1 minute, couple minutes to solve, and then I'll discuss the solution. So before I leave, one quick hint is that uh, this rate is nothing but 1 by symbol time. So from here, you can compute symbol time, and then you can do the comparison based on that diagram. So, so you can do it. I'll give you 2 minutes and then I'll come back.
Hello. Hello.
Okay, I'm getting some answers. So the answers that I'm getting are fast fading and frequency selective. Let's see. So the symbol time here will be 1 by 2k. So that is 0.5 millisecond. And so I can compare that PC coherence time is less than symbol time, which means that the channel changes faster than the time it takes to send the signal. So this means that it is fast fading. So this is correct. And the coherence bandwidth is less than the signal bandwidth. So let's say I denote it as BS. So this means that like in the frequency spectrum, the channel will like have different values for different ranges of the transmit signal. So that means it will behave differently for different frequencies. And so this is also frequency selective. So your answer is correct. So yeah, so this is one simple kind of question that you should be able to solve. Like you will have different values, etc. But yeah, you should be able to solve this kind of question. Any doubts? Otherwise, I'll go with this again. So I think three of you answered. I think it's fine. Okay. So this is the main like basic concept of this. The rest is like further, improved calculation on the same topic. So let's say let's say we do a question on Doppler shift. Sorry, any doubts? Okay. Uh, so Doppler shift, we have already studied that Doppler shift. That is the Doppler frequency is something like this, right? Fc times v cos theta by c, where what is v? Why did I write it as v cos theta? Because your velocity, that is your direction of movement, and the direction of the electromagnetic wave from transmitter to receiver. So let's say this is Tx and this is Rx. So there can, like you might be moving not in the same direction, but in various directions. So there is this angle theta. And so we'll be looking at the component of the velocity in the direction of transition. So cos theta belongs to the range closed interval -1 to 1, which means that depending on the direction of movement, my Doppler shift can vary from Doppler shift will belong to the closed interval minus fc times v by c to fc times v by c, right? Which means we can define this quantity Doppler spread to be the range of this, right? So this will be 2fc times b by c. So we are defining it as a range of the shifts that can happen in frequency because of Doppler effect. So that is 2fc v by c. And this quantity is very important. So let us do a problem with regard to this quantity. So let's say you are told that like your communication system, you're devising communication system, and let's say it's a dual band operation of the system. Let's say 3.5 gigahertz and 5 gigahertz, right? So it should be able to operate in both bands, and uh, and so it should be able to operate in both bands. And you are told that uh, like Tx is, let's say in this diagram, Tx is static, stationary, and the Rx is moving, right? Actually, I drew it the other way. Doesn't matter. Let's make Tx moving, Rx stationary, or both can be moving. The relative velocity is what matters. Doesn't matter. And let's say the magnitude. You're told that v is equal to something like let's say we are talking about bullet trains, so something like 500 km, 500 kilometers per hour, right? Uh, so, so you are asked that. So you are asked what Doppler spread. So you are asked essentially what is the maximum Doppler spread that needs to be handled. So you want your receiver to work properly for both these bands, for both these frequency bands, when the transmitter is probably moving at like 500 kilometers per hour. So, so what is the maximum Doppler spread that you can have? So for maximum, so Doppler spread, let's say denote it as BD, Doppler spread. The formula is 2 times carrier frequency times B by C. So for maximum Doppler spread, so let's say if I have to take a max of this, uh, the velocity is known, right? But the frequency, then the carrier frequency, we need to take the maximum possible carrier frequency, right? Worst case. So what is the maximum possible carrier frequency here? We have two bands, 3.5 and 5 gigahertz. So it's 5 gigahertz. So let us just put in the values. 2 times 5 gigahertz. So 5 gigahertz is 10 to the power 9, right? And V by C. So V is 500 kmph. So 500 into 5 by 18 meter per second divided by speed of light, which is 3 into 10 to the power 8 meter per second. So somebody, can you do this calculation and tell me? I just made up the number, so I don't know the answer. I can try on my calculator. I hope this logic is clear, right? Because you want to figure out what is the worst case Doppler spreading that you can get in the frequency domain. So this is the worst case possible. So I am getting it to be something like 4.63 kilohertz. Somebody can verify and tell me. This kind of calculation you should be able to do.
Yeah, answer is correct. 4.62.
Okay, okay,
Uh,
okay. So then any similar question also you should be able to handle that. Let's say you are now said that, well, uh, like you can handle variations of this question if you know this concept. So not repeating them in the interest of time. Uh, so similar notion, you are asked about spectral widening and coherence time and all that, right? So you know that this is the Doppler spread, or you can also call it like spectral widening, because essentially your spectrum gets spread out a little bit because of this Doppler effect. You can also call it spectral widening. And so the coherence time, so then you are asked the coherence time of the channel. Coherence time of channel. So how does the coherence time, so this is this quantity TC that we have talked about earlier. How does the coherence time depend on this Doppler effect? So I'm not going into the derivation again, but there is this Jake's correlation model where essentially the expected value of the channel, channel at some time t, and for a certain delay profile tau, and then so if you take correlation with some time t plus delta t and same delay profile tau, so here you will get some term which is proportional to some value which is proportional to the zeroth order Bessel function of this quantity 2 pi fd Doppler spread times delta t. So you're essentially trying to see what is the time correlation between so you essentially have the same like same delay profile, so your multipaths and all of that has no change much, but you are just a second. So your multipaths have not changed, but you are trying to and you are trying to see how the channel is varying with time. And that you can measure, if you can, for relay fading channel, it can be derived that it behaves like a Bessel function of the zeroth of the zeroth order or something like that. So essentially this function J0
Sir, one thing, sir, here we are not considering the tau. Actually, we are considering the tau is the same. Delay is same.
Yeah.
So we
Yeah,
we are considering only the instant of time, only time.
Yeah. So like by delay profile, what I mean is you have this transmitter TX, and you have receiver RX, right?
Yeah.
So by delay profile, what I mean is, see, there can be multiple paths from TX to RX. There can be direct path, and there can be like reflected paths. This path.
Non-light of sight,
non-line of sight. Yeah. So all of these will have different values of delays, right? So this will be some tau 0, tau 1, tau 2. So essentially this, like this, all of these will have some delays associated with them. And so all of that stays the same, but you are just looking at the channel at different instance of time. So that is defined by this Bessel zero function. So this is a function of the Doppler frequency, FD. And so actually, so what we try to see is when this Bessel zero function, J0 of what value is equal to 1 by root 2. This is, an important, this is essentially our parameter that if the channel changes by 1 by root 2, then the channel has changed significantly. When channel correlation, like when the channel correlation drops to 1 by root 2, that means the channel has changed significantly. So you can actually solve, so this is like a standard function. So there are tables for it, and you can solve, and eventually, if you substitute everything, you will get that so essentially J naught of this 2 pi FD TC. So this is the definition of coherence time actually. That coherence time is when the channel correlation falls to 1 by root 2. So if you solve actually using standard solvers, you will get this value TC equal to 9 by, so this is explained in Sir's lecture also, Doppler frequency, right? So this is the value that you put. So now we have already calculated, okay, we calculated directly spectral widening, but this is nothing but 2 times FD, right? Because this is FD. This is the maximum Doppler FD. So, so FD will be nothing but something like 2.31 kilohertz. So you can calculate the coherence time accordingly. So can you tell me the value of the calculator? I hope this logic is that essentially FD is this just V by C FC max, and so you can just plug it into this formula, and then you will get the coherence time. So as you can see, coherence time is inversely proportional to Doppler frequency. So the faster your vehicle moves, higher is Doppler frequency, and that means your channel fluctuates fast. Your coherence time is lower. So that is the logic.
Sir, how this 2.31 kilohertz?
This is half of this, right? I told you, like it's a kind of continuation of same problem only. So Doppler spread. So this is the formula for Doppler frequency, right? V by CFC. Yeah. So
4.63 divided by 2.
yeah.
Okay.
We're trying to find like what's the worst case coherence time, or the minimum coherence time. So that will be this.
And sir, how this TC equals to 9 upon 16 pi FD?
I just explained, right, that this Bessel zero function, if you solve, so like I don't have the solution here, but like this is a standard function, like it cannot be solved analytically, it has to be solved numerically. So
Okay.
if you put this value TC equal to 9 by 16 pi FD into here, then you will get J0 of 9 by 8, right? And that value is 1 by root 2. So this is like the solution for this equation. So if you have to solve this equation, if you have to find out so that is the definition of coherence time. That, what is the value of delta t, what is the value of the time difference for which your channel correlation falls to 1 by root 2. Because see, if you put delta t equal to 0, which is, there is no time difference, then by definition J0 of 0 is equal to 1, which means that the channels are perfectly correlated. And well, delta T infinity, obviously J0 goes to 0. So at this value, 9 by 8, J0 of 9 by 8 is equal to 1 by root 2. So solving for that, you can get this value that TC is equal to
Okay, okay,
9 by 8, 16.
okay.
This is, I think I'm getting something like 78 microseconds. What others can confirm. So it's simple calculations are there. So if this is clear, then another question that comes up is hop rate. Hop rate to avoid fading. So in GSM system, you try to hop between different frequencies. If your channel fluctuates, you just try to move to a different frequency band and hope that the channel will be good, right? So what should be the hop rate? Like after uh, like what should be the number of times per second that you will switch from one frequency to another frequency for this channel? And so for that, actually, the uh, hop rate is actually equal to. So essentially, you know that the channel, you know the coherence thing now, TC. So you know that after 78 microsecond, my channel is going to go bad. Like, so what happens is we measure the channel at time t, and then by the time t equal to, like, by the time t plus tc, we know that the channel estimate is going to really not be any relevant anymore because my channel has already fluctuated. So I need to move to a different frequency, and like I need to find the difference part of the spectrum. So that is why hop rate is equal to 1 by coherence time. So in T, because after TC seconds, we are hopping frequencies. So if we do unitary method, then we are hopping frequencies one time in TC seconds. So the hop rate is 1 by TC. So I can simply plug in this value, 78 microsecond, and I'll get the hop rate. It's coming out to be 12.9 kilohertz. Like kilo hops per second, maybe something like this. So these are some like
Sir,
some
it is kilo
questions.
hops per second, no?
Yeah. Or like, I hope I got the calculation. Yeah, I hope the concept is clear that after TC seconds, you have to hop frequency. So you have to find another frequency band. So you have to essentially switch frequencies at this rate. So this is for, specifically, this is for legacy GSM system. Uh, So, so now you have like another kind of you know uh, another kind of problem here, which is 1 second. So you have a vehicle, right? And so because of Doppler shifts, we have this channels fading, right? Doppler shift means that channels will, fluctuate and all that. So, so we can calculate the number of fades per second actually. So Doppler shift depends on the velocity of the vehicles, right? And the velocity of the vehicle follows a certain distribution, which is something like yeah, 2v e to the power minus Gaussian like distribution is there. 2v by v to the power minus v by v whole square, something like this distribution is there. But anyway, so this velocity has two key, data points. One is this threshold velocity, so threshold velocity is the maximum velocity after which, the channel starts fading. So this is threshold. Threshold, writing in brackets for fading. So you want your, your vehicle. So you want your channel to be, so your probability of fading is essentially probability of fading is essentially probability that your vehicle is crossing the threshold of velocity, something like that. And then from statistical distribution of your vehicles, you have VRMS, where RMS stands for root mean square. Root mean square implies that you are taking, let's say various measurements of velocities, so VI. So your VRMS would be if you sum over all VIs, sum over square of all VIs. So let's say V1 square, and this holds for time T1, that your vehicle velocity is V1, and dot dot dot, similarly Vn square, and then your time is Tn. So your vehicle velocity is V1 for time T1, V2 for time T2, Vn for time Tn, plus T2 plus T1 plus, let's say, dot 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 plus Tn. So you are first taking square, so you're squaring the velocity, and then you are taking mean of the square, and then you are taking root over. So it's root mean square, right? And so you are trying to compare these two values. And so there is one key parameter here, rho, in standard notation. This is essentially this V threshold divided by V RMS. You're trying to find out this ratio. And this ratio determines a lot of things. So it determines the number of times a channel goes into fading, and it determines also the expected fading duration. And there are, like, in the lecture itself, I'm just writing down the formulas again. Refer to the lecture for the derivation. The number of times a channel goes into fading is root over 2 pi Doppler frequency FD and then rho e to the power minus rho square. And then T fade, the time duration of one fading is e to the power rho square minus 1 divided by root over 2 pi Doppler frequency FD times rho. So you are told that essentially that the vehicle, whatever pedestrian, whatever, your signal source is moving at a velocity v, which has a certain distribution, probability distribution, and you are provided the threshold of v, which is required for fading. The minimum value of v at which you can say that the channel begins to fade, and then you are also given or you can calculate the RMS, the root mean square velocity.
One thing, sir, can you repeat the what is the threshold velocity for fading? Just one time repeat.
It's like after, like, if you cross the threshold velocity,
Then
essentially
channel will go under the fading actually.
Yeah, then channel will go, then will start fading.
Okay, that is the maximum limit of velocity or correct
Yeah,
channel.
yeah. So
and sir, one thing that sir, one thing that can you tell what is the physical significance of VRMS actually? That is the analytical procedure.
Physical significance is that you can control, like, let's say VT you can control from your channel, you can calculate from your channels. You are measuring the channel across various times, so you know the value of VT, let's say. That
VRMS.
You can you know the value of VT, let's say. So VRMS you can control. You will, like, if you know your channel, you will know that what VRMS you should set.
Okay.
So VRMS is what you have control over, because you control at what speed you are moving or at what speed the vehicle is moving, right?
Okay, yeah.
So you can set VRMS accordingly. Let's say you are operating a factory floor and you
according to my system requirement actually, what one I want.
According to system.
Okay, thank you.
So you can solve small problem, like, let's say you are told that you are setting VRMS to be VRMS you are setting to be this 0.5 times V threshold, right? You are choosing this value of VRMS. Then you are asked to compute this number of, so this is essentially number of fades per second, and this is time duration of one fade. So what is the duration for which the channel remains under fading? So you are told that VRMS equal to 0.5 times the threshold. So what is the value of rho, which is the threshold, divided by VRMS? What is the value of rho here? The value of rho is 2, right? And so you can just put the value of 2 and get the answer here. So if I'm continuing the same question, so I already know the value of Doppler frequency, which is this 2.31 kilohertz. So let me write it again. Kilohertz. 2.31 kilohertz. So can somebody just tell me the answers? Like, you just have to plug in FD and rho into this formula and just tell me the answer. So what is NT? So this answer has to be reported as an integer. So you will tell me the closest integer value. and also P field. You just have to put in calculator. There is nothing fancy here. Instantaneous or average duration of one head? Average duration. It is average. Instantaneous will vary. So this is average duration. I'm getting this value to be 212 and P shade, let's see. This value I'm roughly getting to be 4.63 milliseconds. Can somebody confirm?
NV is equal to 212. It is correct. Okay.
Okay. Thank you.
And fading I will.
One has to memorize this formula. Your choice. You can either memorize or you can derive it during the exam. Whatever helps. I think it's better to memorize some formula. Otherwise, you have to for every question you have to go from first principles and do the derivation, and that is possible, but it will take a lot of time. So for sometimes it might be better to just keep a cheat sheet of formula. For example purpose, that's all. So this was essentially the same concept, Doppler spread, and that uh, that can lead to one question after other, and it's all related. I hope you got the answer for T-Fed as well, time figure. So this is there in the lecture notes also. So that is where I took it from as well. Okay. Any other doubt if you have? Otherwise, I'll do a few more questions. But if you have any particular doubt, please let me know. Some questions are very straight from the lecture, so you can do them. I'll do quickly one typical type of question. So let's say you are given an AW, you're told that for a certain AW, like for a certain modulation type, AWGN behavior is AWGN probability of error, PE, AWGN probability of error. You are told that in AWGN channel, the probability of error is something like alpha e to the power minus beta gamma, right? You're given something like this, where gamma is instantaneous SNR. Instantaneous SNR. So if gamma is the instantaneous SNR, then the probability that you will receive a bit in error, receive a symbol in error is something like this. Alpha e to the power
Sir, it is minus
beta.
beta into gamma.
Gamma, yeah.
Okay.
Where gamma is the instantaneous SNR. So this is the formula given to you for AWGN channel, additive white Gaussian noise channel. I hope we are all familiar with that. So now you are told that what is the probability of error for? So you are asked what is the probability of error for relay feeding. You are asked that what is the probability of error for relay feeding, and you are told that average SNR for this signal that you are sending, average SNR, you are denoting it as capital gamma. You are told that it is, let's say, 0 dB or 10 dB, let's say. Right? Now we can make it 0 dB. 0 dB. 0 dB is the average SNR. So, how do we compute this kind of thing? So, firstly, so whenever there is dB, typically first step you do is, let us at least compute it in linear scale, right? So, this is, in linear scale, 0 dB is nothing but 10 to the power 0.0, which is 1 watt. Not watt, sorry. This is SNR, so it's a ratio. So, gamma is 1. And the Rayleigh fading PDF, so the PDF of Rayleigh fading, actually let's just make it general. Let's just like kind of write a general formula. So you are told that the average SNR is gamma dB. So the Rayleigh fading PDF, you can just put in whatever values and get your answer, but let's derive a general formula. Rayleigh fading PDF, what does it look like? The Rayleigh fading PDF, the gain that is, you are taking modulus of the channel square, which is equal to the gain. So the gain is distributed something like this. As a function of SNR, it is distributed as 1 by gamma e to the power minus gamma by like small gamma by capital gamma, where so this is the exponential PDF, right? Gamma is nothing but expected value of the. So in Rayleigh fading, the gains are exponentially distributed. So so the SNR distribution is like this.
Sir, what is this capital gamma? E of gamma, E of small gamma.
Yeah. So this is the not E, like, sorry, I should write expectation or the average SNR, right? Small gamma is instantaneous SNR and average SNR is capital. Actually, I've written it as gamma dB. So this may mark this that this is gamma linear. So in your question, you will be given as gamma dB. So you have to convert it into linear before writing this. So this, just be careful. So gamma linear, how will you calculate? It will be 10 to the power 10 to the power 0.10 gamma dB, right? So this is how you can convert from dB to linear. So so if you actually calculate this probability of error, like for relay failure, so you're trying to calculate the average probability of error, right? So so you have to just kind of weight this. You have to do this computation essentially. You have to integrate over gamma the error probability as a function of SNR times the PDF of the SNR and over gamma. So this will be something like this. We know this is error properties with respect to AWGN. So this is this quantity alpha e to the power minus beta gamma, and then this is subject to Rayleigh failing. So there is fluctuation in SNR, and so that fluctuation depends on this function. So the PDF of received SNR is this. And so you compute this expectation and you will get, the final probability of error for a relay channel. So can somebody tell me the answer? Simple integration exercise, I think. I think it should come to be alpha divided by 1 plus beta times gamma linear. Gamma. We're talking about linear. This should be the answer. So you can the quick derivation. So depending on your question, you can just plug the values and so this, I hope this is clear. This is one kind of question. Now let's do another important type of question, which is a power delay profile of a link, or gain delay profile. It's also called gain delay profile of a channel. So as I was explaining that, like in a channel, there are multiple paths, right? There is line of sight and various non-line of sight paths. And so different paths have different delays and different channel gains, right? So you are typically, if you are asked to characterize a channel, you will do it like a power delay profile. So you will write the different paths with their gains and channels, right? So we'll typically have a reference path, a zero delay, and the power also you take it as reference value 0. And then you have various other paths like it's 1 minus 2 into 6 minus 9 7. Typically, longer delays means the path is longer, and so the power will also be typically less. And some very long path. Let's talk to the- So you are provided some kind of power delay profile. I've made up the numbers, so I really whatever answers we have to calculate and see.
Excuse me, sir.
Yeah.
Sir, will this video will be uploaded today only on?
Yeah, I'll upload it today.
Okay.
But
Okay.
I'll upload it. I'm not sure when you will get it. So that part I don't know. Whenever NPTEL provides, you will get it. I upload it from my end today.
Okay, sir, because I'm unable to attend it further right now.
Okay.
So,
Okay.
then how I will get it?
You can leave. I'm sure all the other students are also getting the YouTube link, right? Because
sir? What, sir?
YouTube link is being provided to you, right? Because we are
Oh.
uploading it in the sheet, and every student should be getting access to the YouTube link and the Drive link for the notes. So that is not under my control, but I can my end I can share the YouTube channel and all, but this should be provided to you by NPTEL itself.
Yeah. So, can you please put that link here, sir?
Okay. I have put the playlist in the Zoom chat, but as I said, this NPTEL should be providing you. So
yeah, but even if we go directly on YouTube and paste this link, so that will also give us.
Yeah, this is the playlist. I've provided the link of the full YouTube playlist. So I'll keep on uploading every week. I'll keep on after taking this session. I just upload the recording to the playlist.
Yeah. So we will get it on YouTube only, na sir, directly.
Yeah, you can get it on YouTube. But as I said, NPTEL should be emailing you the video recording links. So you can it is on YouTube.
Okay. Okay, sir, please send that link on this forum.
I've sent the link in the group chat. Please have a look. And meanwhile, let me continue. I don't have much time.
Okay, sir.
It is in the group chat.
Yeah. Thank you, sir.
Okay, so you are given this kind of a power delay profile of a channel. So different parts have different delays and different gains. And you are asked to first compute mean delay of the channel in, let's say, microsecond. So how will you compute the mean here? So by default mean here is a weighted mean. So you will weight the delays so the weights here are the powers of the channel. And so you will compute the weighted mean. So before computing the weighted mean, we should first convert all the dB scale values to linear scale. So we can quickly redraw the table with values in linear scale. So delays microsecond. So let us convert power to linear scale. Can somebody tell me the values quickly? So the delays I'm writing 0, 1, 6, 7, 13, 20. And you have to tell me these values. So 0 dB is 1. 1 is 10 to the power minus 0.2. And somebody tell me the value. This you have calculated. So I'm getting 0.6. 0.63, and then 6 is minus 9. So So 10 to the power minus 0.9. So that comes out to be 0.126 roughly. And then this is minus 10. So this is 10 to the power minus 1. So this is 0.1. This is 10 to the power minus 1.5. You should be quick with these kind of calculations. And 20 is 10 to the power minus 4. That's 0.0001, I believe. Right? So in linear scale, we have converted. And so what we need is the mean delay. So mean delay is nothing but summation tau I times, these gains or the powers Pi divided by summation over all of the things. So can somebody plug in the values and quickly tell me the answers? Like, so this is like 0 into 1 plus 1 into 0.63 plus 6 into 0.126 plus 7 into 0.1 plus 13 into 0.032 plus 20 into 0.0001 and divided by, I'm taking just a weighted thing. So divided by, I just add all of these power values up, right? Set all of these power values up. So it will be 1 plus 0.63 plus 0.126 plus 0.1 plus 0.032, 0.0001. So if I calculate the denominator, so this I'm making to be the numerator is getting it to be 3.32 microseconds. So this is the mean delay, right? So now you are asked the RMS delay spread. Or denoted as sigma tau. So you are asked to calculate the RMS delay spread. So what is like the diversion? What is the dispersion in these delay values? And this is defined as the kind of like standard deviation. So this is like, firstly you take the standard deviation is variance, which is, you take the delay square and take a mean of that minus. So this is the standard deviation definition, right? So, like for any quantity, sigma is equal to expectation of x square minus expectation of x whole square. So this is the variance, and then once you take the root, this is sigma. So similar definition is there. So over here, you are asked to calculate the value of this in microsecond. So you know the value of tau bar, which is 3.32. Now we have to find this thing, which is tau square bar. How do we find tau square bar? So for this, again, it's a weighted average. So we take tau square, tau I square times the gains, and then we sum over the gains, right? So this denominator we know, we have summed over the gains earlier because it was the same denominator. So it is 1.8881. So let's not do this calculation again. Numerator, let us calculate. This is 0 we can ignore. 1 square. So 1 square into 0.63 plus 6 square into, I think second point was 6. So 6 square into 0.126 plus 7 square into 0.1, right? 7 and 0.1. 13 square into 0.032 plus 20 square into 0.0001. Right? So this numerator you have to calculate. And this value comes out to be, let's calculate and see. If somebody has done it, please let me know. Six square, 6 square into 0.126 plus 0.1 plus I'm getting it to be 15.514 divided by 1.881 equal to 1.8881, which is equal to 8.2217. So this is microsecond square, right? So let us quickly now calculate this sigma tau quantity. Sigma tau is equal to square root over uh, 8.217 minus this square, so 3.32 whole square. So let us see. I think I have made some mistake because this will give a negative value, right? Uh, yeah, this is. Can somebody check this? Okay, I might have taken wrong set of values or something like that. Or I might have made a calculation error. Let me calculate the numerator again. No, it is correct. It is correct. This is the approach, but again, maybe like I was taking random values, so maybe the choice of values was wrong. maybe choice of values was wrong. So this will actually give some kind of imaginary number. Let's see if I can fix this quickly. But anyway, I hope you got the idea. And so this is how you will calculate the sigma tau. If instead of minus 40, let's make this minus 20. So then this becomes 0.01 and this also becomes 0.01 and then this also becomes 0.01. So some calculations will change. This will become this will become 1.898 and numerator will become this into the numerator becomes 2.702 and so this value becomes 1.42 1.42 microseconds and this also changes to 1.898 and the numerator changes to, let's see, 0.63 plus 6 squared into 0.126 plus 7 squared into 0.1 plus 0.032 plus 9, this will be 19.474. Minus this divided by this comes out to be 10.26. I think this will now have a solution. Yeah. Probably made some calculation mistake earlier. 10.26 minus 1.42 squared. And this is coming out to be 2.87 microsecond, which is microsecond squared. So this value is important. This is like the RMS delay spread, and the delay spread essentially determines other important quantities. Concept is clear, calculation right only, but I wanted to show the calculation once actually. So this is because there are some other things that follow. So the coherence bandwidth. So you see that earlier we discussed Doppler fluctuations. So the Doppler frequency and the spectral widening, the Doppler frequency determines the coherence time. So if you remember this equation, the coherence time depended on the Doppler frequency. Similarly, the coherence bandwidth depends on the delay spread. And how does it depend? So there is, in the lectures, there is this model which is called white sense stationarity and uncorrelated model, uncorrelated scattering model. According to this, the coherence bandwidth, so you are asked the minimum coherence bandwidth. This is the question in kilohertz. In kilohertz. How do you calculate that? So the minimum coherence bandwidth is actually given by a formula, and I'm not going into derivation again. It's similar kind of Bessel function is there, which you solve, and you get this value. So this is given by this value. So from the power delay profile, you have this, RMS value of the delay, and this you plug it in here to get the coherence bandwidth. So can somebody tell me the answer in kilohertz? Let me do this by myself once. This let's say 5 into 2.87 microsecond inverse. So I'm roughly getting it like 69.7. This is 69.7 kilohertz. So that is the coherence bandwidth, right? So now the question is, so this is the coherence bandwidth value, and so question is, we are provided that symbol rate. So we are asked what is the minimum value of the symbol rate for which equalizer is needed. Equalizer required. Why do we need equalizer? Equalizer is needed when channel is frequency selective, because then we need to kind of equalize between different frequency bands, right? So equalizer, what does an equalizer do? It is when the channel is unequal in different frequencies, it adjusts the, so at the receiver, we have to do some adjustment so that that unequal frequency is, that unequal value is kind of balanced. So if you have some channel, some signal X of F passing through channel H of F, so before you kind of, so this is a very crude diagram. So before you actually receive it as Y of F, you pass it through an equalizer, let's say E of F, where, so this is basic digital communication. This is where E of F is roughly equal to 1 by H of F. So you are trying to balance, you're trying to cancel off the impact of the channel. This can be one kind of equalizer, but you will only need it if H of F is unequal across different frequencies. So essentially, by this question, minimum RS, minimum rate, symbol rate for which equalizer is needed, you are trying to say that what is the minimum symbol rate for which my channel is frequency selective. My channel is frequency selective. So, so for this actually, see, you need that your symbol rate RS, which is, so your symbol time taken to transmit the symbol is, time taken to transmit the symbol should be less than should be less than 10 times the delay total, like the delay RMS. So if your signal is taking more time to be sent, that means your channel will become progressive. Your channel will become frequency selective. And so for that, you need RS, your symbol rate, which is 1 by TS. It has to be greater than 1 by 10 times sigma tau. And so you know the value of sigma tau, delay this value. You can just plug it in here and get this minimum value. So this will be RS greater than 1 by 10 times 2.87 microsecond. And so this answer will be I'm getting it to be approximately, it should be half of the previous value. So 34.8 kilohertz. So you don't want to be sending your signal to why 10 times? Because kind of you can calculate, like this, the derivation is there in the lectures, but just an like kind of tentative number that like if your delay, if if your symbol takes 10 times this value, then when you convert to frequency domain, then see, if symbol time, if delay spread is more than if delay spread is like this thing, right? If like essentially if your delay spread is more than if your delay spread is high, sigma tau greater than TS by 10, which means that you are sending one signal and you are sending another signal, let's say, with some delay from two. So at the receiver, you are combining signals coming from two paths. So one coming here, another coming here. So you will have interference. So if your path delay is too much, then symbol sent at t equal to 0 and t equal to ts will have some interference. So that is the idea. Like that is the idea. Like it's somewhat difficult to explain right away, but your inter-symbol interference will be there. So 10% overlap will be there between two consecutive copies of the signal. So this will be, let's say, this duration is also symbol time, and this duration is also symbol time. And because of this delay, you will have inter-symbol interference of 0.1 symbol time. So 10% overlap will be there. And more the delay, so let's say it's more than 10%, let's say sigma tau is greater than is equal to TS itself, then 100% overlap will be there between previous and current signal. So you will have, this is known as inter-symbol interference. This is known as inter-symbol interference. So the signal that you transmitted before will start interfering with the current signal. So that is why this tentative value is taken, that if 10 times if your if your symbol time is within 10 times this, so this is like the if you are sending your signal at a rate higher than this, then your channel will become frequency selective in nature. So you cannot send signals at so if you want frequency flat channel, then there are some restrictions. You cannot send signals greater than this. So actually, another notion of frequency selectivity is this thing, so that consecutive signals, consecutive symbols that are sent should not overlap, or should have minimal overlap. So if there is overlap between signals, then there is inter-symbol interference, which happens because of frequency selective channel. So this this you want to avoid. Because if delay is 0, if sigma tau is identically equal to 0, then you will have one signal and then another signal. But if there is some delay, then because of delay, this signal will be pushed to a certain extent, and then you will have overlap. Because by the time that next signal is being sent, then there is some overlap between the receiving of previous signal and current signal. So you want to minimize that overlap. So that is also reasonable. G of 0 and G of 9/8, there is nothing much to explain, because this is a standard function. Bessel function is okay, there is some delay. This is a standard function. So Bessel function of 0th order. And so this has like well-defined values. So so like you can actually, this is actually defined like this. So J0 of 0 is 1 and J0 of 9/8 is equal to 1/√2. So if you forget all of the fading and everything, this is a function, a standard function whose value at 0 is 1 and value at 9/8 is 1/√2. So accordingly, since value at 9/8 is 1/√2, you want, like, so that is why you have defined your function over here, Bessel function, that where was it? That if J0, so you want your channel correlation to remain within 1/√2. So you know that the value at J0 of 9/8 is 1/√2. So if you put 2 pi FD TC equal to 9/8, then you'll get TC equal to 9/8. There is why it is like this, because it comes through the derivation that you know, this channel correlation across time is in the form of Bessel function. And then this is a standard function with standard values. So okay, I think my time is up. I will end the session now. And, thank you.